My name is Mikael Mugi, and I'm a researcher at the Princeton Institute for International and Regional Studies, which is hosting the event. We are delighted to organize today's conversation in partnership, our first partnership with the Department of Astrophysics. Thank you, Michael, so much for your support. I would also like to thank our other co-sponsors, the Department of Anthropology, the Department of Spanish and Portuguese, and the Program in Latin American Studies. This event would not have been possible without the incredible help of the Brazil Labs manager, Carol Dopp. I think she's not around. Thank you, Carol, for putting this together. I will be brief in my remarks, and we'll soon pass the mic to our amazing guests. Let me introduce our incredible lineup of speakers for today, and then I will detail the format of the event. Lia Medeiros is an Einstein Fellow at Princeton. As a computational high-energy astrophysicist studying black holes at the frontiers of the universe, Lia's research takes space as the ultimate laboratory where theories can be tested in the most extreme environments imaginable. Lia is a highly accomplished scientist. Before joining Princeton and the Department of Astrophysics, she was a member of the Institute for Advanced Study here in Princeton and a National Science Foundation Astronomy and Astrophysical postdoctoral fellow. Vinicius Duarte is a physicist at the Princeton Plasma Physics Laboratory. His research tackles scientific challenges to help develop nuclear fusion as a safe, clean, and virtually inexhaustible source of energy. An award-winning researcher, Vinicius is the recipient of the 2023 Department of Energy Early Career Award and a member of the editorial board of Physics of Plasmas, one of the most prestigious journals in his field. Joining Lia and Vinicius as a discussant, we are very happy to have with us Adriana Petryna. Adriana is a professor of anthropology at the University of Pennsylvania, where she also directs the MD PhD program in anthropology. She's the author of the absolute classic Life Exposed: Biological Citizens After Chernobyl. Her most recent book, Horizon Work at the Edges of Knowledge in an Age of Runaway Climate Change, has received several accolades, including the Diana Forsyth Prize and the Robert Textor Prize by the American Anthropological Association. Lia, Vinicius, and Adriana, it is truly wonderful to have you with us today. As for the format of our event, our guests will speak for about 15 minutes each. Adriana will follow, taking a few minutes to offer comments and questions. Lia and Vinicius will then respond, and after that, we will open the floor for discussion. Please join me in giving our warmest welcome to Lia, Vinicius, and Adriana, and then we will hear from Vinicius.
Well, thank you so much. Thanks, Mikael, Rodrigo, João, for the invitation. Very happy to be speaking here today and informally discussing this very promising and interesting topic of nuclear fusion as a possibility to produce clean, safe, and abundant energy for the humankind. So I'll touch on some overarching aspects of the current research and the possibilities that can be opened by it. So let me first give you a broad overview of what the humankind usage of energy looks like over the past 200 or so years, so since before the industrial times. So you see that 200 years ago, we were basically using biomass. Then we started picking up coal, oil, and gas, which now account for the bulk of our consumption. That tiny fraction up there comprises nuclear, solar, biofuels, wind, hydro. Brazil is very lucky to have a sizable fraction of its energy being generated by hydro, but that's definitely not the case for most countries. So we need to think about climate change. We need to curb emissions of greenhouse gases. We want to limit the average temperature increase by 1.5 or 2 degrees Celsius since our reference from pre-industrial ages. So we need to come up with creative solutions, and it's not just one single solution. There might be many. And today I'll be describing one of those, which is a subset of nuclear. So what is nuclear fusion? So let me give a very simple, but I think it conveys the basic point. So nuclear fusion is not more, not less than the mechanism by which stars generate their own energy. So all the energy we receive from the sun comes from nuclear fusion. So as the name suggests, it comes from the merge of nuclei. So the example I'm giving here is deuterium and tritium, which are different forms of hydrogen under some circumstances and conditions, typically high pressure, high temperature. They can glue together, and nuclear fusion happens, and you have the products of that reaction. For this specific reaction, the products are helium, which is a gas that doesn't cause any trouble. We naturally have helium in our atmosphere, and neutron that comes out with a lot of energy. So the figure on the right shows if we could hypothetically put the products and what the elements we start with on a scale, we would see that the products are lighter than what you start with. So using this famous Einstein relation that which converts a deficit of mass into energy, so that means we have energy release in this reaction. So that's the type of energy we want to harness in a laboratory and eventually build a power plant using that principle. But to harness that type of reaction, we need to use a very hot medium called plasma. So what is a plasma? What is this this medium that allows for nuclear fusion to take place? So if you start with a solid and you heat it up, eventually you get a liquid. If you keep heating, you get a gas. That's the molecular structure of each one of those. If you keep heating a gas, then eventually you get this plasma, which it looks like a gas. However, it's different in the sense that you have free charges. So some electrons escape from their trapping nuclei. So let's put like this, it's a more complicated and hotter gas. So that's the state of matter, let's call it that, that we need to make nuclear fusion. Although it's not present in our daily lives that much, like usually we deal with the first three, but plasmas actually comprise 99% of the universe that we know. So there's a lot of the universe we don't know, like dark matter, dark energy, but what we can see, more than 99% occurs in this form of plasma. So how would a nuclear fusion power plant look like? So it looks complicated, but let me break this down. So essentially, we would have a machine or a reactor that would confine this plasma. So the plasma is a very hot medium. It would spin in this machine. The machine would confine it. Eventually, we would get this type of reaction. A very energetic neutron would escape, and it would heat a fluid, which would move a turbine, and this whole the second half to the right is very similar to what we have today for a thermal power plant. So you move a turbine, and eventually that goes into the grid as electricity. So that's what we envision as a nuclear fusion power plant that it's still in experimental stages. It's not ready yet, but that's the idea. Let me differentiate between what is fission and fusion, because there's a lot of confusion sometimes. So both are types of nuclear processes, and both can release energy and be harnessed as an energy source for us. Fission we already have for a few decades now. So since this is the Brazil lab, I chose to show the Angra 1 and 2 fission power plants in Rio de Janeiro, Brazil. Fusion is already there. Fusion that I'm presenting about, it's still being studied There's a lot of advances being made over the decades, but it's not ready yet for commercial purposes. What would be the advantages of nuclear fusion, especially over fission? So I'm listing here what I believe are the four greatest advantages. The first is that nuclear fusion is very clean, since it does not involve the emission of CO2 or it doesn't involve any radioactive waste that has a long life. It's intrinsically safe. Unlike fission, it does not rely on a chain reaction. So what happened in Fukushima or Chernobyl would never happen in a fusion power plant. The operating principle is different. If something would go wrong, then a fusion power plant would just shut down automatically. It's intrinsically large scale, on a gigawatt scale. So just for comparison, the Itaipu power plant, which is the second largest hydro power plant, which is in the border between Brazil and Paraguay, it has an installed capacity of 14 gigawatts. And a fusion power plant would be more or less of that scale. So it's very big. And it's virtually inexhaustible in the sense that the fuel, I mentioned you can use, for example, deuterium, tritium. It could either be extracted from seawater, or it could be produced or bred within the reactor. So I think there is no exaggeration in saying that fusion has really the potential of changing our civilization. The problem is that it's just very complicated, and we've been doing research on this topic since the early 50s, and though there has been a lot of progress, it's still not there yet. Let me show about what has been happening here over the decades. So, as I mentioned, this type of research of trying to use nuclear fusion as a peaceful source of energy started in the very early 50s, and Princeton was a pioneer on that. So this photo here is the Princeton Plasma Physics Lab, where I work, which is managed by Princeton University since the early 50s, but it's a Department of Energy National Lab. It's just 3 miles in that direction. It's close to the Princeton Hospital, and since it started during the Cold War, you see that the lab is all surrounded by woods. Like it was classified top secret for the first few years. This is the largest experiment we operate at. It's called a tokamak. So it's what you see in the center here. It's a prototype for a nuclear fusion reactor, and everything you see around are paraphernalia to heat it up. And I'd like to advertise that we do open public tours in the lab. If you access this link, pppl.gov/engage with us tours, there are guided tours which are very nice, and you can see the facilities and the lab as well. So what is the status of the research on nuclear fusion? So as of now, as we speak, the largest single experiment is being built in southern France. It's called ITER, which in Latin means the way, and it stands for International Thermonuclear Experimental Reactor. First you come up with the acronym, then you come up with something for it to mean, right? And it's going to cost perhaps more than $30 billion US dollars, and it's approximately 75% built. This is an aerial photograph of the whole facility, and what I'm circling here in pink is just one person for you to have the dimension of like how large this the facility is. It is so expensive that countries come together to build it together. It's a consortium between US, Japan, Korea, Russia, India, and the EU. And it will reach temperatures of over 10 times hotter than those in the center of the sun. So the center of the sun is at approximately 15 million degrees Celsius, and this is going to be it will reach 200 million degrees Celsius. So just for context, ITER will look like something like this. Not to the right. It's not a power plant yet. It's an experimental tokamak reactor. And over the past couple of years, we saw a huge increase in the private investment in fusion, and we saw this emerging fusion industry, which indicates that the technology is not that far. And over $6 billion US dollars have been invested in the last couple of years in fusion startups. And that amount is growing. So it's not that we're very close, but it doesn't look that we're very far either. So let me change gears here to pass the baton to Leah. So I mentioned about one application of plasmas, which is nuclear fusion. Okay, that's the holy grail of research in fusion, is to make nuclear fusion a viable, commercially viable source of clean and abundant energy. But plasmas are much more than that, and I wanted to show some beautiful natural occurrences of plasmas. One of them is what happens in the surface of the sun. So those eruptions called solar flares. Eventually, those particles can reach Earth and lead to those beautiful phenomena that we see close to the southern pole and the northern pole, the aurora borealis and australis. And another very beautiful occurrence is what happens in nebula. That's the parts of galaxies where stars are being born, where they're formed. And yet there is another fascinating plasma object, which is the accretion disk, this material that surrounds black holes in galaxies. The conditions there are so violent that everything is in the plasma state. And with that, I turn it over to Leah. Yeah.
Okay, well, hi everyone. Thank you so much for coming and hanging out with us and learning a little bit about astronomy and plasma physics. Thank you also so much to the organizers for the wonderful introduction and also for inviting me to come talk with all of you. I'm really honored to be part of Brazil Lab event and really excited to get to know all of you a little bit better during the discussion. So the way that I've structured my talk is I'm going to first introduce a little bit about my actual research, and primarily I'm going to be focusing on the result that you see here. But after I kind of introduce a little bit about my work, I'm going to talk about kind of the side project that I've been working on and its relationship to climate science and how we maybe could use astronomy as a way to communicate about that. Okay. See, now it's going to play, of course. So anyway, this is what the result will be eventually. Okay, so I am a member of the Event Horizon Telescope. I've been part of this collaboration since before it was a collaboration. This movie is going to take you through a tour of all of the telescopes that participated in the very first observations with this collaboration. The idea here is that this is effectively a virtual observatory. We observe radio waves, and that's what we use to actually make our image. And we needed such high resolution that we actually needed an Earth-sized telescope. And there's just no way to build that. Even, $30 billion would not give you an Earth-sized telescope. And so what we do is we use a technique called interferometry, where we use a bunch of telescopes that are spread around the world. They all come together, work effectively as a team. Everybody looks at the same source at the same exact time. We collect all of that data, and we're able to use that data to generate an image. But what's important to keep in mind is that we cannot cover the Earth in telescopes. You'll see that there's a lot of this blue stuff, right? Very hard to float a telescope. And so we can't cover the Earth in telescopes, which means that there's a lot of missing information. Okay, and so there are very sophisticated algorithms that we have come up with that effectively guess what's going on in the regions where we have missing information, and that's one of the things that I'm going to be highlighting later on in my talk. But before I get to that, it's also really important to keep in mind that the Event Horizon Telescope collaboration is not just a bunch of telescopes that are working together, but it's really a bunch of people that are working together. And so this is my personal favorite picture of us, because we were in Hawaii and it was amazing and beautiful. We have many other pictures, many that are more recent, that a lot more people are involved in and included in because it's more recent and the collaboration has grown. This is still my favorite because, I mean, it's Hawaii, right? So anyway, there's over 300 people in the collaboration, and I really do want to emphasize that it really is a global effort, and the nature of the project itself requires that it be a global effort because we do need the telescopes to be spread all over the world. So these are the two main results that you might have seen from the Event Horizon Telescope collaboration, perhaps in the news. The one on your left is the very first image of a black hole that humanity ever saw. This is an image of the black hole in the center of the M87 galaxy, or Messier 87, and this was published in April of 2019. On the right is the second image of the second black hole that we published, and this is actually our black hole. So every galaxy, we believe, has a supermassive black hole at its center. This is our supermassive black hole that's at the center of our own galaxy. We are currently going around this black hole even as I am giving this talk. And so this one has also a name. It's called Sagittarius A star. This black hole and I are on very close terms, so I call it Sag. Most of us do. Sagittarius is pretty long, kind of a mouthful. This particular graphic here, I made this for the press release, actually. And so the relative size scales of these two images are the actual relative size scales of these two images that you would see on the actual plane of the sky. What do I mean by that? This black hole is really, really small compared to this one, 1,000 times smaller. But it's also about 1,000 times closer, which means that from our point of view here on Earth, it looks a little bit different, a little bit bigger than the other one. However, to really illustrate the physical sizes of these objects, I'm also comparing them to features in our own solar system. So this little dot here has the diameter equal to the diameter of our sun to scale. And the white circle that hopefully you can see is the orbit of Mercury. So Sagittarius, or Sag, fits really comfortably inside of the orbit of Mercury. It would fit really comfortably inside of our own solar system, even though it is 4 million times the mass of our sun. So very compact. M87, however, this little circle in here, this is the orbit of Pluto. This dot here, this is the probe that has been generated or created by humanity that has traveled the farthest in history, right? So humanity has been sending things into space for a really long time. This is as far as we've gotten, which is pretty small compared to the size of this black hole. So it's billions of times the mass of the sun. Okay, so what I want to shift our attention to now is a new algorithm. So my collaborators and I have generated a really large data set of simulations that you see here. These simulations effectively take into account everything that Vinicius just told you about. So they take into account the plasma as it swirls around the black hole and eventually falls into the black hole. We've generated this whole kind of space of images, and we use it as a training set for the algorithm. And so the idea is that the two images I just showed you did not make any assumptions about physics at all. But the image that I'm going to show you that was generated by this algorithm uses some basic building blocks that it learns from these simulations as a way to fill in the gaps where we don't have data in a way that is physically motivated. And so I'm going to visually show you what the algorithm does. We think about all of these images as a image space, right? So there's this space of images, and the algorithm will learn what I like to call building blocks, right? So it learns certain patterns in the images. What it's really doing is it's learning how different parts of the images are correlated with each other, and then it uses those correlations to fill in the gaps. If you are in physics or math, this is principal component analysis. That's why it's called PRIMO. It's principal component interferometric modeling, which is a rather tortured acronym, and I apologize, but this was the best that we could come up with. I didn't even come up with it. A collaborator came up with it, and this was the best that our collaboration collectively could come up with. Okay, so this is what the actual building blocks look like visually. And so the idea is that you can add and subtract the little building blocks of images in such a way that you can approximate any image that lives in this broad kind of image space. And so I can add and subtract these to approximate this image, which is just slightly blurred from the original simulated image over there. I originally had only used free building blocks, and you don't really do that great of a job, but if you use, let's say, 20 building blocks, you do a much better job approximating the structure over there. And so what the algorithm actually does is it uses these building blocks and it fits those building blocks to the data directly and generates the image that I'm going to show you shortly. So this is the M87 image that the EHT originally published, and then this is what comes out of the Primo algorithm. And what you might have remembered from 2019 is that when that first image came out, it was on like the front page of every newspaper. It kind of went viral, and a lot of people had a lot of fun with it, right? So there was a lot of memes, a lot of fun things all over the internet. My personal favorite meme is this one, lovingly created by some random wonderful Twitter person that I tried to acknowledge over there. And so of course I wanted to get in on the fun a little bit as well, right? And so this is my new version, where, you know, Homer now has a diet donut, which is the least appetizing form of donut that I could possibly imagine, but at least we're keeping him healthy for years to come so he can continue to entertain us. Okay, so back to the actual science. So this image has a little bit of what we call hyper resolution, so there's a little bit of resolution that's a little bit more than what the instrument could technically really give us. And so we have, what did I do? So we have a new version of the image that apparently you will never see. I promise we tested these things. It's still working here. I'm so sorry. Okay, anyway, I'll just keep telling you about it. Eventually it'll come back up, I'm sure. So, we have a new version of the image that is similar to the one that I just showed you, but it's blurred a little bit more such that we've suppressed this hyper resolution, and we are actually limiting the resolution to be the maximum resolution of the array, and this is what that looks like. No, it's not. Oh, no, it is. Good. Okay, cool. So this is the new, Primo machine learning version of the image. And you might be wondering, okay, so what? Why do we want to make this image? Sure, fuzzy orange donuts are very fun, but what's like the take-home message, right? What do we actually learn? Unfortunately, I don't actually have time to tell you anything about that, but I will give you a teaser and hope that if you're interested, you will ask me more about it in the time that we have for discussion. And so this is just one example of one of the reasons why it's so exciting to make these images in the first place. And that's because we can actually use these images to test fundamental physics. So we're in Princeton, everybody's heard of Einstein, right? And so Einstein has this theory of gravity, and that theory of gravity predicts a very specific black hole. And so what we're actually doing is that we use the size of the donut to test whether or not the black hole that we have in space is consistent with this very specific black hole that is predicted by Einstein's theory of gravity. And if we find that the black hole in space is not consistent with this very specific black hole that Einstein predicted, then we need to have a really fundamental paradigm shift about how we think about gravity itself, but also how we think about black holes. This image is an artist's image, but I absolutely love it. So I wrote a popular science article about how we use black holes in space as laboratories for the IAS, and they commissioned an artist to draw her vision of a black hole laboratory. I think this is gorgeous, but my favorite part of it is that if you look very closely, most of these scientists are female. But it's not like in your face, right? It's not the first thing you notice, it's subtle. I really enjoyed it. Okay, so this brings us to Brazil Lab and the event that we have today. So black holes will never be useful as sources of energy. They will have absolutely no effect in our daily life and our ability to deal with climate change. However, since this is Brazil Lab, and since so many people here, I think, are interested in the Amazon and interested in climate change as a whole, I wanted to also discuss briefly kind of a bit of a side project that I've been working on. So I have a disclaimer, which is I am not a climate scientist. They are the real experts, and you should always listen to them over me every time. So with that being said, I'm going to tell you stuff anyways, but again, listen to the climate scientists. So I was a NSF Astronomy and Astrophysics postdoctoral fellow at the Institute for Advanced Study for 3.5 years. And as part of this fellowship, there's an expectation that you will create a educational/outreach project. And my project focused on middle and high school students, specifically low-income students, many of whom are actually refugees. And so I was teaching in both English and Spanish, which I'm Brazilian, so, you know, learned some Spanish, which was good. And these are the kids I was working with. There's a greenhouse, which is very fun. Here they're looking at the actual spectra of the sun through these little tools. And here we're actually making a 2-scale model of the solar system. Here's a planet, and you can see that there's a tiny little student way over there, because most of space is actually empty space. And so, so I was teaching them about radiative transfer, and that naturally led to a discussion of the greenhouse effect. And so if you will humor me briefly, I will try to give you just a really brief introduction, which I hope will just serve as an example of how we can use astronomy to talk about climate science. I'm not going to go into the details here, but the idea is everything we know about astronomy we've learned from light, pretty much except for neutrinos and gravitational waves, but I'm going to ignore them for today. And my philosophy comes from Mary Poppins, which we all know is a wonderful philosopher. A spoonful of sugar makes the medicine go down. And the idea here is that astronomy is really fun, especially with kids, right? Kids love black holes. They're so weird. They're in very fun movies, right? They're in, you know, popular science things and so forth. So when you're using astronomy, you can kind of, I don't know, it's not as political. You know what I mean? So much of science has been politicized that I think that a lot of times it can be useful to use something like astronomy, which isn't as politicized, to have this discussion. And so that's kind of my philosophy. So anyway, if you want to know the details of how we use light to learn about the universe, you can ask me. But what I'm going to do is spend the next 30 seconds showing you an actual example of how we can actually do a real calculation with like 12-year-olds and have them calculate for themselves the effect of greenhouse effect. Sorry, the practical effect of the greenhouse effect. So we can calculate the percentage of the sun's energy per time intercepted by a planet, and that's going to be the energy that's going to heat up the planet. So here we have the sun, we have a planet, light from the sun is going to go out and reach the planet. This percentage of the light, effectively the cross-section of the planet, is the percentage of the light that is going to give us the energy that will heat up the planet. We can actually do all of these calculations. I'm not going to go into the details, but effectively the total energy per time from the sun divided by the total surface area of this really big sphere, where the radius of the sphere is the distance between the planet and the sun, and then multiplied by this little cross-section of this little circle here, which is the cross-section of the planet. And when you actually do all of that out, this is the equation. And then there's this handy-dandy astronomy equation called the Stefan-Boltzmann law, which is going to tell you that the energy per time that the planet receives is going to be equal to this, where this T is the temperature of the planet. And so you can solve for that and get the temperature of the planet. Obviously, this is all super fast, but the point of this is that I think that it can actually be really useful to have students go through the actual math and the actual equations and actually calculate things for themselves and find for themselves that there's some weird behavior when you ignore the greenhouse effect. So specifically, if you use that equation to calculate the temperature of Venus, you will find that it should be 130 degrees Fahrenheit, and that the Earth should be 42 degrees Fahrenheit. The actual temperature of Venus is 900 degrees Fahrenheit. So drastic difference. And the temperature of the Earth is 57. So again, drastic difference. This discrepancy, of course, comes from the fact that both of these planets have atmospheres. Venus, we know, has a really thick carbon dioxide atmosphere, so thick that we do have a really significant runaway greenhouse effect, which is what causes this drastic difference in the temperature. Okay, I'm like 2 minutes over. I'm so sorry. I tried so hard to stay on time. But anyway, thank you so much. And these are some discussion points that are maybe useful, maybe not. But thank you guys.
Adriana? Yes? Mm-hmm.
Do you want me to turn this off?
Oh, no. It's
Okay, you can keep it on. Yeah.
We can just hypnotize the audience.
Let's do that. All right. Well, thank you so much for the invitation. Thanks so much for the opportunity to be here and think with Leah and Vinicius about their work, and also about their larger implications for how we imagine other kinds of worlds. And I also take this as a unique opportunity to host a dialogue between two very accomplished scientists from the Global South and a larger scientific and lay public. I myself am an anthropologist. I've worked on issues that have also taken people to very different worlds, whether it's the aftermath of a nuclear disaster in Ukraine and among persons who suffered immense trauma as a result of it, or whether it's the climate crisis, in which I work with scientists and also the people who work on the front lines of the crisis, specifically wildland firefighters, who are trying to contain these wildfires, but they're also trying to make sense of their abrupt and often novel extreme behaviors. And one surprising finding for me was that the extent to which wildfire science and wildfire modeling have not really kept pace with the changing circumstances in which we all find ourselves. So as I hear you both speak, I'm thinking about edges of disaster as well as of leading edges of discovery. We can call them leapfrogging moments in science, where what has only been imagined or theorized becomes real and even harnessed. And it's questions like these that I think animate this event, called Imaginable Horizons. And so these horizons imply scientific operations that exceed any single or simple process of controlled experimentation in laboratories, for example. They're about the uncontrolled or unknown that requires very distinct forms of attunement, multiple ways of knowledge production, and engaged research processes that are happening at multiple scales and among multiple constituencies. And I'm super interested in how you both are working at these complex edges, and specifically for Vinicius on the challenges of developing nuclear fusion. The big edge question is instability and nonlinear behaviors in plasma physics. And I know most of your talk was about the applied side of things, but I'm interested in how you think about this edge, and specifically how you think about the concept of experimentation. How do traditional ideas of experiment break down, particularly when the object under study is plasma, this volatile thing that cannot be contained? And I'm also curious about your sense of, or your use of perhaps physical intuition or intuition in understanding instability. So things that are beyond the science that you bring to the science, right? And then the second question concerns the move from the theoretical to the applied, which is often depicted as pretty seamless, linear process. But you describe something that is much less linear. So how does your work at larger scales, the tokamak, for example, add knowledge, but also perhaps even revise notions about what the nature of plasma is? In this, what I think of as a kind of iterative process, do we arrive at a different notion even of what it is? And then at what level of knowledge about its behaviors, what level of knowledge about its behaviors would be adequate enough to make the case for fusion energy, that in fact it can be exploited? So is there uncertainty that is associated with having more knowledge about the thing itself? And then going back to the edge question, this time for Leah, I just want to know what the experience was like to look at an image for the first time that you've generated of a black hole. What did it mean to look at something that was only theoretically predicted and that you could now see? And also, again, about these edge questions, in this case, how you navigate invisibility. And I'm particularly interested in the algorithms. So how do you train them to remain open in what is inherently invisible? How do you have to maintain, let's say, a certain agnosticism to underlying models for them to be open to new discoveries, to understandings of variability, to surprise? And how do you know when you're constraining those models too much, those training sets too much? And then on the question of collaboration, going back to this wonderful picture in Hawaii, you mentioned that the Event Horizon Telescope isn't actually a telescope. It's more like an agreement between many telescopes to work together as a team. So I would love to hear you talk about collaborations, whether it's the smaller collaborations on the theory side or the much bigger ones on the observational side, and what kinds of human complementarities make that process work. And also in terms of the different sites and telescopes around the world, collaborations at an enormous scale, have there been any surprising aspects to the collaborations? What do we learn about it for science, perhaps for larger publics? Finally, inasmuch as both of you are coming from the Global South, how do you see the Global South in your work and in your thinking? What can you say about exporting Global South thinking, if there is such a thing, elsewhere, such as here? And also, I suspect that this event was called Imaginable Horizons because in circumstances with limited visibility, horizons are not metaphorical here. They are, in fact, things to be created and tested for how well they tame complexity and uncertainty, or bring us closer to the novel or the unknown. So I just want to thank you for letting us in on this all-important process.
I think you can.
Yeah, thanks a lot, Adriana. Thanks, everyone, for sticking in as well. So, I mean, you touched on many key points, and so let me first discuss the instabilities and the nonlinear behavior you alluded to. So that's, in fact, one of the gaps that need to be closed to make nuclear fusion a viable source of energy and commercially viable. And I think that resonates well with your other point, which is how do we tackle that? Like, should we just have the same old conventional way of thinking and using tools, and I think that goes beyond and touches on diversity of workforce. So not only race and gender, but like, I think the geographic diversity is very important as well. So people to come on board with very different thinking angles. So people that address the problem with fundamentally different approaches, and that has been a very active discussion in the field. And not only the diversity aspect, but the energy justice aspect of it. So let's say in a couple of decades from now, this is a working source of energy. Are only rich countries going to be able to have it? Are they going to sell for a very expensive price to the global south? You know, so those are. I think this is being thought about very seriously over the past couple of years, which I think is great. This was not even on the agenda before. So regarding the participation of the global south on trying to harness fusion as an energy source, it comes in very different levels. So China and India, they do it very aggressively in terms of investments, but in Latin America, unfortunately, we have some serious history in studying plasmas and fusion, but the investments have not kept up, especially over the past decade. So we do not have a good representation in the field in terms of like Latin America. Like, I'm the first one and only one in my department from Latin America, and that's reflected throughout the institutions in the field.
Okay, thank you so much. That was really fascinating, and I really appreciate that you took the time to get to know us and get to know our research and to join us in this discussion. I'm going to start in chronological order based on the things that you brought up. And I believe your first question or comment from me was about the experience of actually making that first image. And I get this question quite frequently, actually, and I actually really enjoy answering it because it was kind of a once-in-a-lifetime experience in many ways. So I consider myself a theorist or a computational astrophysicist, but there was something about this observational exercise that was just so exciting that I, put on my observer hat, let's say. And so I traveled to Boston to the Black Hole Initiative and actually spent the whole summer there in 2018 for some personal reasons as well, but one of the big reasons was that I knew that that's when we would be making the first image and I wanted to be involved. I wanted to be in the room where it happens, right? And so, I learned how to use the other algorithms and I was there, right? And we all kind of got together and we all pressed the button at the exact same time. And we had been working on this for so long, right? And there was kind of an understanding within the collaboration that this was the first time that we had turned on the instrument, right? We just press the button to turn it on. It probably isn't going to work, is honestly what we thought, right? Because we had only 8 telescopes, and here I'm ignoring the fact that several of our telescopes are actually made up of a bunch of smaller telescopes. I'm just treating them as one. But we had 8 telescopes at 6 geographic locations, and only 5 locations could observe M87. And doing interferometry with only 5 telescopes is quite challenging. Doing interferometry at 1.3 millimeter wavelength, which is the wavelength that we observe at, is incredibly challenging. From an engineering point of view, right, there's so many obstacles and so many things that had to go right to make this happen that a lot of us were like, okay, this probably won't work the first time. We'll probably have to work on this and keep observing for a few years. And I kid you not, it was 10 seconds. We pressed the button, 10 seconds later we saw the image and we're like, what? And it was just I didn't believe it, you know what I mean? It was crazy excitement in the room, right? Because everybody's just like, oh my God, that's it, that's the image, that's exactly what we'd been predicting and what we'd been simulating and what we'd been preparing for. But it was so easy. It came out of the data so quickly and easily that honestly, we had an hour-long discussion about, yep, this is probably injected data, right? Somebody is trying to make this a test. And test whether or not we are able to reconstruct this fake data that they created. And they gave us a really easy one to start, right? They really don't have a very high confidence in us. And it took us months to really believe that nope, this is the actual data, this is what the actual black hole did. And it was just so kind to us in a way that science rarely is. Looking back, I think that there were many emotions, as I've kind of tried to explain. But also, I think that relief was a really big part of the emotions as well, right? Because you've been working your whole career, which I was still in grad school, so my whole career was not very long. But you've been working, right, so hard on this project that has a really high risk of failure. And it is very relieving when it's oh, okay, we have a result. I will maybe get funding for the next year, right? So it was really, really exciting. By the way, all of this happened in June of 2018. And we did not publish the image until April of 2019, which means that then we had to be completely quiet about this huge life-changing event that had just happened to all of us. And what's particularly crazy is that I had to do my PhD thesis defense 2 weeks before the image came out, and I could not say anything about the work that I had been doing for the last few years because it was embargoed. And many people on my committee were, personally interested in any possible results from the EHT, and they kept asking me these questions that I kept flat out dodging. And eventually they were like, oh, it's not that you don't know, you just can't tell us. And it was crazy to watch their, in real time, their expressions and body language of coming to terms with oh my God, there's gonna be an actual result, you guys have actually done something. So that was also really fun. Okay, that was very long-winded and I apologize. The question about invisibility I think is really interesting. So black holes themselves are fundamentally invisible. They do not emit light that humans can detect. However, the image is also not light that humans can detect, right? And so what you're seeing is not light from the black hole itself. What you're seeing is light from the matter that is around the black hole. And the fact that there is a dark spot in the middle is due to the fact that some of the light has fallen into the black hole. And so fundamentally, we are not seeing the black hole. What we're really seeing is the effect of the black hole on the surrounding matter. And so that's how seeing the invisible kind of plays out, if that makes sense. I feel like I'm talking too much and I apologize. The question about how agnostic this machine learning algorithm is, I think, is also really, really important. And I really appreciate that you asked that, because that's one of the things that I had to remove from my talk due to time constraints. So the way that my personal philosophy about this is that when we were first making that first image, it was crucial that we be completely model agnostic. This is something that all of us felt very, very strongly about. Myself included. And so the algorithms that we use do not make any physics assumptions. So they are not based on physics in any way. So the first images are completely model agnostic. We worked incredibly hard as a whole collaboration on those results, and I feel very confident in saying that those results are very robust. What do I mean by that is that there is no way that that image is not a ring. We are very, very certain about that. Given that we have robustly proven that that image has to be a ring, I then personally feel confident in moving forward making that assumption. Does that make sense? And so the algorithm itself doesn't actually care about the physics. It's pretty dumb in terms of the physics. What it cares about is the image morphology. It's the shape of the image. And so given that I've proven that it's a ring, it's okay to make the assumption that the image morphology is going to be a ring. And so what the training set does is we go out of our way to include as many different shapes of images as we possibly can, including, in particular, the variability that you brought up, which is a very good point. But again, the real assumption that we're making is it's going to be a ring-like image, and that I think is quite fair to do given what we've seen from the previous results. I feel like I'm talking too much, so I'm going to stop. But there are other things that you brought up that I do have comments on, but I want to be respectful of everyone's time.
Okay, thank you so much. We have some good 20 minutes for Q&A. So we'll collect a bundle of 3 questions and then we'll direct them to Leah and Vinicius. Wants to start with a question or comment?
I can start.
João?
Okay, no, thank you so much. This is truly remarkable. Thank you for the work you do and, your generosity in explaining to us, the lay man and woman here. And it's so fascinating. There are so many dimensions that Adriana also brought up that I would like to pursue. Please feel free if you want to revisit some of the points. But Vinicius, I was very intrigued with the countries that are supporting this, right? US, Japan, Russia. So it's interesting. It's a different kind of diplomatic space of sorts. So I'm just curious about the geopolitics underpinning this project, and also where does the governmental and private funding come together, conflict, where do you see tensions or possibilities? So geopolitics and financing, public-private. And those images are just phenomenal. It's artwork, literally. So I just wonder, your own inspirations, you have this incredible knowledge, but how do you see art in this? Does art inform your perception? I'm just curious about art informing your perception, or you seeing something of art in those images.
Okay, Jakob.
Thank you so much. It was really, really inspiring and fascinating, especially as a non-scientist who does not understand all of that immediately. Opening up. Thank you. I have 2 questions that. One is to Vinicius. I'll be very curious to hear more, like you mentioned, also like corporate private investments coming in. And my question here would be like, how will that impact like the distribution of fusion? And you touched upon that already, but I'd be really curious to think about, so what are we going to do about intellectual property and then access in the end? And the second question, I'll be very interested here. You showed that image from Hawaii. And there's this telescope. Is it the one on Mauna Kea? And how are you dealing with the question of like indigenous land rights? Because I think there was a strong contestation around that telescope. And I'd just be curious, like how is that discussed within a scientist community? Yeah.
Lucas, you had a question?
Yes,
Yeah.
yes. I second the praises. Like, thank you. This is amazing, amazing conversation. So yeah, for Vinicius, I'm thinking about like the larger infrastructure challenges that the thermonuclear fusion may encounter. So let's say if we have a breakthrough kind of thing like tomorrow, what can we expect in terms of like challenges of transporting or that energy, like keeping it in batteries, like storage we know there's a lot of going on with battery developments these days. So I mean the whole energy field is like passing through like a boom in investments and research. So maybe it would be interesting to hear a little bit more on that like secondary layer of the applied thing here. And for Leah, we were in that workshop from Brazil Lab a few weeks ago. Really amazing also about like the latter part of your research, I guess, in terms of like communicating about climate crisis and so on. And I remember like you talked a lot about a lot of interesting stuff that here you were not able to touch because of time constraints. So if you could talk about more, also if you had like new ideas since then, because I guess in that workshop we were really focused on Brazil, but there was also like this interesting connections with like the U.S. society and like groups working here and in Brazil. And I think that there's a lot of us in the room interested in those sorts of discussions. So yeah, thank you.
Great, thank you, Lucas. So we turn it to you.
Shall I start? Yeah, so the geopolitics of fusion is really fascinating. I mean, that's one topic in and on itself. It's amazing. Let me tell you a very quick story on how things happen to be. So right after World War II, Juan Domingo Perón, then president of Argentina, hired a few Nazi scientists and placed them in southern Argentina, in an island right in front of Bariloche today. One of them, Richter, he claimed that he did nuclear fusion on a small tabletop device. He believed it, but he was wrong. But nonetheless, the president of Argentina announced that on the radio broadcast, and it made the cover of the New York Times. Argentina does nuclear fusion for energy. So that sent shockwaves throughout the world. Like the Soviets and the Americans were looking at fission and fusion from a weapons perspective. They were not thinking that fusion could be harnessed for a peaceful purpose, for generating electricity. So that sounded the alarm, and Lyman Spitzer, a professor of astrophysics here at Princeton University, he was going on vacation, and then he thought, how can that be possible? How can we confine a plasma to generate fusion? On his vacation, he wrote a proposal for the, I think it was called Nuclear Energy Commission in DC. He got funded, and that's how the Princeton Plasma Physics Lab was established in 51 or 52, highly classified in the beginning. But then, so the Soviets were doing it, Americans were doing it in secrecy, but after a few years, people realized it was just very difficult. Nobody would do it by themselves. So in 58, there was in Geneva, Switzerland, there was a conference called Atoms for Peace, and that's when the Soviets and the Americans undisclosed their research in nuclear fusion. And it's surprising that, like, in the height of the Cold War that was happening, nuclear fusion has always been an avenue for scientists, for exchange of scientists between the US and the Soviets, even during the Cold War. And in fact, ITER, the big experiment that is being now built in southern France, the one that is going to cost $30 billion, it's a huge diplomatic effort. So the initial negotiations were done by Gorbachev and Reagan in Reykjavik, Iceland. So even during the Cold War, they were collaborating on that, and they were pawning up money for this joint effort. So let me just, I'll pass the to Leah, but let me just connect this with the public-private partnerships that were asked by two of you. So fusion research has been largely done by the public sector, like funded heavily. The level of funding now is around $1 billion US per year in the US only for fusion. But we're seeing this emerging private fusion industry. And that's very healthy for the whole system. It's good for everyone. So it's not only one company here, one company there. It's really an ecosystem of industry. So one industry is supplying a certain material to another industry, which supplies another material to make a fusion reactor. So it's the whole enterprise. Now, how will that work? That was Lucas' question. Like, let's say somebody has a breakthrough tomorrow. What's the intellectual property? That's a very active field of discussion. It's not clear. So I'll give you an example. There's a private company, which is a spin-off of MIT. It's a very big one called Commonwealth Fusion System. They had to come up with a whole legal framework to continue to collaborate with the university. So it's not very simple. There's a whole new set of regulations that we need to come up with because it's something fundamentally new from what was going on before. So this is a very active discussion, but I think it's a consensus that everyone welcomes the good competition of private companies. In the end, the government funding is there to kickstart the effort, and then let the private industry do then. There's always room for research. So, for example, in fission, which is a well-established industry, there's still a lot of research going on to support that industry. So that's how I would frame it. Sorry that I took too long.
It's amazing.
Okay, so your question first about art. I think I never really thought about it in quite that regard, like in quite that way. But I actually really like that question. So I've always really enjoyed art in many different ways. It's always just been a part of, kind of my hobbies. And I think that the way that I personally have been kind of exercising that part of my personality in my work is actually by choosing the colors for simulations. So it's a very practical answer to your question, but that's exactly what it is. So if you guys remember the little poster that we had,
Yes.
I had a lot of fun with this. This is actually a free color image. So there's 3 different wavelengths shown here, and the different wavelengths are shown in different colors. None of them are actually visible, so I just picked colors for them. And I picked the relative intensity of them just right. There's actually a little bit of red right here, which on the screen you can see a little bit better than printed out. And here, it's actually a combination of blue and green such that you can see part of it that's white, or close to white. And that's because those features in the image are bright in both the green, the wavelength that is not actually green, but I'm showing you in green, and blue. And so that's kind of one outlet I think that has been very fun is the visualization, both for talks for the scientific public, but also for the media and public outreach. I really enjoyed that. And that does kind of relate to the image itself as well. So this is radio. Radio doesn't have a color. The human eye cannot see it. And so the reason that it's orange is that it took us 10 hours of meetings with, not everyone, but a significant subset of the collaboration where we all argued for our favorite color, and the people that liked orange won. So, that's so funny. At no point in the last 5 years that I've lived in Princeton that occurred to me, but you're so right.
See?
This was before I was at Princeton.
Discoveries here.
Exactly. So anyway, so there is part of it is art in terms of, the color map that we as scientists choose to share our data with the public, which I think is a big part of astronomy as a whole, since so much of astronomy is not done in the visible light. We always need to choose the colors that we're going to use to depict it to other humans. Are we answering all 3 questions
Yes,
at a time? Yes? Okay. So the question about indigenous land rights, that's a really, really important and really good point, and I appreciate you bringing that up. So for those of you who are maybe not aware, there's been a fairly large scale, I'm going to call it a conversation that's really downplaying it a lot, about the indigenous land rights in Mauna Kea, which is one of the big islands in Hawaii. So there's a lot of telescopes in Mauna Kea. Astronomy as a whole is actually quite limited in terms of where we can put telescopes, because there's a lot of different factors that go into what is a good place to put a telescope that's completely outside of human control, such as you need a mountain that's high enough to be above the water vapor in the atmosphere. It makes a huge difference, right? You need the weather to be good, right? Because there's no point in putting a telescope somewhere that's going to be cloudy and rainy all the time, right? So all of these things, it just so happens that Mauna Kea is one of the best places in the entire Earth to put a telescope. And so there are many telescopes on this mountain. This mountain has really important religious significance to indigenous Hawaiian community. And so there have been really significant protests over the last decade or so about this. There's supposed to be, again, not necessarily the right terminology, but there was a planned addition of a new telescope to this mountain, and really, really large scale, many dollars for that. And right now, as far as I am concerned, my view of the problem is that the consensus of the astronomy community is that that telescope should not be added to that mountain. That is, I think, how most of us feel, is that we need to put it somewhere else, because it is so clear that the community has been really, really negatively impacted by this and has been very hurt by this. And it's all part of this larger scale colonialism, effectively, that happened to Hawaii. And in many ways, this mountain and the telescopes on it have become a symbol for that larger fight and the larger frustrations of the indigenous community. I should say that there are a couple practical things that we as a collaboration have tried to do. They are definitely insufficient. I've had a lot of kind of deep discussions with a good friend of mine who is an indigenous Hawaiian and also an astronomer and also part of the collaboration. And so we've chatted about this a lot, right? And, he's pretty active in kind of the activism within the Hawaiian community about like, hey, there's like some cool astronomy that we could like do too, but like, there needs to be a balance of how do we work together and not against each other and so forth. One of the things that the collaboration did, which again is not sufficient, but I do think it could be an interesting starting point for a larger conversation, is that people from the collaboration worked together with scholars of the indigenous Hawaiian languages to name the black hole in M87 with a traditional Hawaiian name. So the culture is such that the way that things are named is by taking other existing words, putting them together into a new word. So you create a new word for this new thing. And that, I think, was a really beautiful collaboration, and it gave a sense of ownership and participation to the indigenous Hawaiians, which I think is really the least we could do. I think there's more that we should do, but it, I do think, had at least a positive impact. So the name of M87 is Powehi. It's spelled Powehi, which I think is really beautiful. And anyways, sorry, that was also very long-winded, but it's a really complex issue that I think is really important. My thoughts on communicating climate change, like what we had discussed in the activism workshop. So I think that it's very interesting in a variety of ways. Part of me hopes that it could be an interesting way to kind of bridge the gap with people who are maybe on the side of the political spectrum that is very against learning about climate change, because what I've seen in my personal experience is that even people that in general kind of anti-science, anti-vax, anti-climate change, so forth, are still asking me about black holes and are still interested to chat about black holes and are still like, hey, that was cool. And so I wonder if there's anything that we could do to actually contribute meaningfully to the larger conversation that we're having as a society about climate change with astronomy, right? Because so many people don't even know about the example of Venus, right? And it's very hard for you to argue that Venus has this temperature because things melt. We have sent things there, and they have melted, right? And so there are things like that that I think are kind of interesting in terms of, can astronomy actually contribute meaningfully to this or not? There's also some other issues that I'm personally really curious about and care about, which is kind of the ethics of teaching kids about climate science. I think that we're at a stage now in our society that we should be very aware of the world that these kids are growing up in right now, with what's happening to geopolitics and what's, happening to the climate and so forth. I think that there's a really careful balance that we need to strive for in terms of making sure that they are informed, but also making sure that they have a hope for their future, because they're children, right? Like, they need to be able to have dreams and have hopes and have goals. Otherwise,
Imaginable horizons.
yeah. Otherwise, it's we're really not helping, right? And so I think that there's also some larger kind of ethical dilemmas that I personally am struggling with in terms of how do you communicate about this in a way that is sustainable and ethical, especially when you're dealing with younger students.
I think we have time for a quick round of questions. We have one there.
Yes, thank you. My question for Vinicius is, I guess in Brazil there is Angra 1 and Angra 2, and they build the Angra 3. In comparison, like countries like in Europe, even United States, Japan have dozens of nuclear plants. So my question would be, how do you see the future in Brazil in terms of use of nuclear power for electricity as a source of electricity, and how, for example, that could compensate the huge use of hydropower, that at least in Brazil is very significant. And my question for you is that I was very curious about the algorithm itself. I found it very, very neat, the idea of eigen decomposition. And so I just wanted to ask some questions. First about the data set itself of images. Were these images taken from telescopes in different positions, or some of them were just like part of them like synthetically generated? And so just a quick question about the data set, and also in terms of the model itself, the machine learning algorithm, how did you learn, for example, the optimal size of the eigenbases to decompose your image in these eigenvectors, and also like how it learned the other hyperparameters of the model itself? Like, what are the most important features that your model had to learn in order to fit the data?
More questions? Yes, Vinicius. And then
Okay, to my shout out, Vinicius. So I have a question about political disputes and contestation over fusion. You mentioned something that was really astonishing, that you will be able to generate 10 times the heat of the center of the sun. And I imagine, the kind of playing God argument that it may raise. And we're in a moment where, I think just last year or maybe 2 years ago, Germany shut off all their nuclear power plants, or started to. France is doubling down on the nuclear investments. So nuclear power is still a contested topic. And when we have fusion being developed, not sure if it's going to become a possibility in the short term. The fair decision of investing in it is also a political decision, and is a decision that may, give way to contestation and to dispute. So I wanted just to ask you more about this. What kind of backlash, for example, this decision to invest 25 billion raised? That kind of issue. And to Leah, about you said that astronomy is not heavily politicized. And that's interesting, because in fact, like you don't see it directly as you see with climate change, but there is at least one political dimension in funding, right? That's at least one we could raise, and also how astronomy helps push our horizons further as it creates new or comes up with new findings that we couldn't expect before. Just having the possibility of seeing the image of a black hole, that's not exactly about a black hole, but still communicated as such.
Yeah.
is something that creates new horizons. And I mean, we could talk about many examples of how astronomy made possible, the creation of safe havens for billionaires, space tourism, space militarization, all of that. So I just wanted to ask you about the political dimension in funding for astronomy nowadays. What are the disputes behind it and interests too?
We have one more question.
Yes. So this one is for Vinicius. So actually, almost to the day 11 years ago, I started my undergraduate education back in Brazil, studying physics at USP, which I picked because I wanted to study plasma physics, and that was one of the few departments in Brazil that had an active plasma physics group. And I think I had read a lot about ITER, for example, and the sort of large global effort that the plasma physics community, was engaged in. And it was very disheartening to some extent that my experience there was one of more like isolation due to the funding cuts and those sorts of issues. And luckily I'm here today, but not as a plasma physicist in a different field. And so, in your view, how can you engage with the community of the Global South when so much of the broader plasma physics research community is effectively, decoupled from what these small-scale efforts can actually do? How do you recruit these people? How do you seek them out? How do you give them the proper training? How do you integrate them into these larger supranational collaborations? Do you have any thoughts on that?
Great. Turn to.
Oh,
Yes.
me first? Okay. Okay, so the first question was about the algorithm itself, and I really appreciated that because that's what I usually end up talking about, and I removed all of that. So let's actually talk about what the algorithm is. I know, but I had an equation. I'm so sorry, but I tried to go through it really fast, right? Okay. So first I want to discuss, is this machine learning? Because that actually is a really interesting question that I have kind of gone back and forth on. And I think it's a prerequisite to your questions because it will explain a lot about the algorithm. So when I first started working on this algorithm, I really liked how simple it was and how easy to understand it was, and how it was really just linear algebra, which in physics and math, right, like that's what you take like your freshman year, or maybe even in high school if you're like at a super advanced high school. And so I'm literally just diagonalizing a matrix. And that's something that we've been doing for, decades or centuries, right? And we know what that does so well, and it's so easy to understand. I really appreciated that it wasn't a black box. And so because of that, I wasn't really personally thinking about it as machine learning. When I wrote my first paper on the algorithm, the referee report came back, like, the referee was livid. Like, so upset that I had not mentioned the words machine learning and had not given accurate credit to that community, because this was obviously machine learning. And, in my perspective, I thought it would have been insulting to the machine learning community to call this machine learning because it was so simple, right? And so, to appease the referee, of course, we apologized. I added a couple paragraphs, I added a bunch of citations, and now it's machine learning. And so then when I wrote the next paper, to be consistent with the first, right, I also said, okay, well, this is machine learning. So let's talk about exactly what it is and exactly what it's not. This is not AI, and it's not a convolutional neural network. What this is technically dictionary learning. There is a clear definition for dictionary learning, and this does fall into that definition. The idea is that pretty much any way that you're going to decompose a space of information is technically dictionary learning. People have been doing that for so long, and we never called it machine learning. But now, officially, it falls under the umbrella of dictionary learning, which is kind of under the umbrella of machine learning. And so, okay, so we clarify this really, what I think really well in the paper about, hey, it's technically machine learning, but it's really dictionary learning, it's really just linear algebra. And then we wrote a press release. And the press release, again, says dictionary learning. And then I had an interview with Dennis Overby from the New York Times, and I very clearly explained exactly what I just explained to you guys, that this is not a convolutional neural network, it's not AI, it's actually quite simple, but it is technically dictionary learning, which falls under the machine learning umbrella. And he responded with, great, I'm gonna say it's convolutional neural network and AI because it's gonna get more views. And I'm like, but that's wrong. And he's like, nobody cares. And so the New York Times published that, and then when our image came out, it went a little viral because AI right now is really hot. And so then it became, AI sharpens image of black hole, which is absolutely not what we've done. And so there's a lot of really interesting things that we're trying to navigate here, which are a little new to me, actually. And so I've been having a lot of conversations with experts in machine learning, because again, I've taken classes in machine learning, and I actively made the decision to not do a convolutional neural network because I wanted it to not be a black box, and I wanted to understand every single step of the way. So anyway, all of that is to say that what we are literally doing is that the training set is 100% simulated images. So we run a general relativistic magnetohydrodynamic simulation, which is the simulation that takes into account all of plasma physics and all of general relativity and all of thermodynamics and all of fluid mechanics and you just throw all of physics into a box and a black hole comes out. Oversimplifying, clearly. And then after you do that simulation, you then have to run a radiative ray tracing simulation, which what that is doing is it's asking, okay, I have some plasma, this is what the plasma is doing. Would that plasma be emitting light? What wavelength would it be emitting, and what would that light do as it moves through this curved space-time around the black hole? Okay, so that's what the actual training set is the product of this. I actually ran about 500,000 different simulations for this, so different high-resolution images for this training set. At the end of the day, the final training set that I used for the actual image only had 30,000 images. There are reasons for that we can get into. So effectively what we do is we take PCA of the images, and we use an MCMC algorithm to fit the PCA components to the data directly in the Fourier domain, because PCA and Fourier transform end up commuting in this particular example, at least. Maybe not in general, but at least. If those were just words, it was the words I think that you were looking for, I hope at least, right? Because it actually answers your questions. But the idea is that MCMC is Monte Carlo Markov chain that we've known for a very long time. It's just fitting, right? So I'm just fitting a linear combination of building blocks of images, which are PCA components, to the data directly. Yeah, I don't really have any other hyperparameters other than I allow all of the PCA components to grow together. So that gives us my mass over distance scaling. That's a free parameter in my model. I also allow all of them to rotate together. That will give me the orientation angle of the spin axis of the black hole on the plane of the sky. I also allow all of them to be mirrored, which means that either the stuff can go clockwise or counterclockwise, again. And so all of those are fit for at the same time in this MCMC, and I get posteriors on all of them. Sorry. Politics, funding, right, okay. Very interesting, was it you? Yes, okay. Very interesting point, and I'm just gonna preface this by, my response is going to be very biased and is clearly the response of an astronomer who thinks highly of astronomy, and you should take it with a huge grain of salt, okay? The way that I think about this and the way that I view my own personal choice to focus on this particular area of science is that, to me, I feel like since the earliest civilizations, astronomy has been a part of the human experience, right? The earliest civilizations looked up at the sky and tried to understand the patterns and the movements and so forth, and tried to understand their place in the world. And so I think that, for me, I always think about it as a human experience and a human endeavor, and not as a country-specific political endeavor. One of the things that I also personally enjoy about being part of this field is that historically, this is not a field that tends to get more money during times of war, right? So my dad's an aeronautical engineer, and I always like to point out to him that his field flourishes in dark times in human society, whereas my field suffers in dark times in human society, but flourishes when things are going pretty okay. Which again is obviously an oversimplification, because obviously, supernova are effectively bombs, and so there's obviously, exceptions and examples and counterexamples and so forth, right? But in general, that's just my own very biased kind of self-fulfilling view of this. But practically, yes, right? Like, we need to play politics to get funding. And it is quite tricky to do so, right? And it's also, you know, quite tricky, right? Like, NASA is one entity, and if it has X number of dollars, and then you argue, well, what percentage of that should go to climate science and what percentage of that should go to astronomy? There are ethical arguments to be made that maybe it should all go to climate science, right? Because astronomy is not actually going to help humans, right? And it all depends on like your philosophical view of like what is most important. Is it to help humans or is it to advance human knowledge, right? And it's all very complex, I think. I think that there are a lot of tricky things in terms of, I feel like in many cases, astronomy is the first to go. And I think it's been very depressing for me personally to kind of see what's happened to astronomy funding in Brazil in particular over the last decade. We had done really amazing progress in that regard. We were kind of slowly becoming part of really large-scale collaborations and large-scale projects to build telescopes and so forth. And it's been really heartbreaking to see. I think that, you know, it's always tricky to argue for funding astronomy, depending on who you're talking to, and there's so many different aspects and ways that I think we as a society try to do that. My thought about it is frequently, well, black holes are cool, right? Like, you know, they're fun, right? Like, this is, you know, it's like the spice of life, right? Like, it's the fun stuff. Like, this is just kind of crazy, and it's kind of awesome that we're using a black hole in space to test fundamental physics like a laboratory, right? Like, all of those things are, you know, we're not curing cancer, obviously, right? We're not saving anyone, but it's still, I think, really fun and really interesting, and I think that it does add overall to, like, our collective human experience as a not U.S. society, but as a global society. I don't really know if that answered your question, but it's a complex thing. I apologize.
No, good.
Yeah, sure. Yeah, thanks for the question. So there were more than one question regarding nuclear fission, not fusion, fission. So I'm not a specialist in that, but let me give my 2 cents anyway. So I think, like, broadly, fusion is already too late when we're thinking about climate change. Like, if our goal is by the end of the century have less than 2 meters of sea rise, probably fusion will not be a solution to meet that. It would come after. So I think we need to be not ruling out any source of non-fossil fuels. So we need to go solar, we need to go fusion, we need to go wind, hydro, everything. Now, and there was a question specifically about Angra, the 2 power plants in Angra in Brazil. I think they generate roughly 1% of the Brazilian power output. So it's a big help, but it's very far from being one of the main sources of energy. In Europe, it's much more pronounced. In some countries, it's could be close to half. I think Europe has largely regretted not investing more in fission and relying too heavily on Russian gas. I think that is changing now. There are policies being enacted now to revive and to develop new fission power plants. And fission, I know there's a lot of history and sad history when we think about Fukushima and Chernobyl, but nowadays it's a pretty safe energy source. So there are the so-called 4th generation fission power plants with a very big degree of redundancy and safety, and to the point that it's a great tool now. So Bill Gates, for example, has been investing a lot on that. It is a great asset. Of course, we need to think about stockpile stewardship and all those complicated issues. We need funding for that, but I think that's definitely one of the solutions. And regarding funding, so somebody mentioned, okay, ITER is so expensive, it's $25, $30 billion. But if we put in perspective, it's quite cheap, because if that's, imagine $30 billion over 30 years. That's $1 billion a year, shared by multiple countries. The U.S. military budget is over $800 billion a year. I mean, fusion is peanuts compared with that. So if we think like that, we should be investing more, I think. And regarding the question about how developing countries, and Brazil in particular, could be contributing to fusion, it's a very important and difficult question to answer. So on the one hand, it's very difficult to do fusion research on a university scale. So intrinsically, it's very big, very complex, very costly. So that's why fusion is usually done in national laboratories, like the Princeton Plasma Physics Lab, Los Alamos, Lawrence Livermore, Oak Ridge in the US. You need to concentrate the effort in a place and put everyone there and have one big machine. So it is challenging when you don't have the budget to do that in a developing country. So ways that we've found to circumvent that would be either having smaller experiments with the purpose of training students, but not necessarily contributing to cutting edge research because of the limited resources. So that's one avenue. You train students and then they go on internships abroad and come back. And the other avenue is to send students abroad to work on the biggest machines. While this makes sense on the research front standpoint, there's a chance that those students will be absorbed and not come back and not contribute to further developing fusion science in the country. So it is very hard, and the International Atomic Energy Agency has been discussing this and has been promoting many events to train students in developing countries. So it is an issue.
Thank you so much, dear Vinicius and Adriana. I have so many questions, and I guess this is just a point for us to do a part 2 one day. So thank you so much for being with us today.
Well, thank you.